Alright, let's go. Number 10. Hoag's object. In 1950, astronomer Arthur Hoag was examining photographic plates at McDonald Observatory in Texas when he discovered something that shouldn't exist, 600 million light-years away in the constellation Serpens, a galaxy displayed geometric perfection that defies everything we know about cosmic chaos. The object showed a nearly flawless ring of brilliant blue stars surrounding a dense core of ancient yellow stars, separated by a vast gap containing almost nothing at all. What makes Hoag's object truly unsettling is its precision. The ring deviates less than 1% from a perfect circle. In a universe where galaxy collisions create asymmetric debris fields and irregular structures, this cosmic architecture appears almost deliberately designed. The outer ring spans approximately 75,000 light-years in diameter, composed of young, hot stars actively forming. The core measures 17,000 light-years across, filled with older, cooler stars. Between them lies a 24,000 light-year gap of near-perfect emptiness. The mystery deepens when scientists attempt to explain its formation. The leading theory proposes a smaller galaxy passed directly through the center of a larger disk galaxy, creating an expanding density wave that triggered star formation in a ring. But this scenario requires a precision collision, perfectly head-on, at exactly the right velocity, with minimal deviation. The odds seem impossibly low. Alternative theories involving bar instability dissolution or external gas accretion fail to explain the gap or the extraordinary symmetry. When Hubble Space Telescope imaged Hoag's object in 2001, it revealed something almost mocking. Visible through the galaxy's empty gap is another, more distant ring galaxy. A ring galaxy behind a ring galaxy, as if the universe were showing us it can create these geometric impossibilities repeatedly. What other cosmic blueprints might be hiding in the darkness, their perfect symmetries waiting to challenge our understanding of natural formation? Number 9. PSR J1748-2446ad. On a routine observation in 2004, astronomer Jason Hessels was analyzing radio pulsar data from globular cluster Terzan 5 when he detected a signal that seemed to violate the laws of physics. Using the Parkes Radio Telescope in Australia and the Green Bank Telescope in West Virginia, his team confirmed what shouldn't be possible: a neutron star rotating 716 times per second. That's 43,000 rotations per minute, so fast that its equator moves at 24% the speed of light. This isn't just remarkable velocity, it's approaching the absolute theoretical limit before centrifugal force tears the object apart. Every point on the neutron star's surface experiences gravitational forces roughly 1 trillion times stronger than Earth's gravity, while simultaneously being flung outward by rotation. The object exists in a state of perpetual tension between these opposing forces, balanced at the razor's edge of structural integrity. Located approximately 18,000 light-years away in the direction of Sagittarius, PSR J1748-2446. ISAID belongs to a rare class called millisecond pulsars. Scientists theorize it achieved this extreme rotation through a process called recycling. Mass transferred from a companion star spiraled onto the neutron star over millions of years, each particle adding angular momentum like a cosmic figure skater, pulling in their arms. But even this explanation struggles with the extremes observed. The rotation rate suggests the neutron star's equation of state. The relationship between pressure, density, and composition in its ultra-dense core operates at limits we've never directly tested. What makes this cosmic top truly disturbing is the implication that somewhere in the universe, objects might exist rotating even faster, balanced even closer to the point of catastrophic disintegration, their existence sustained by physics we're only beginning to understand. Number 8. Smith's Cloud. In 1963, a young astronomy student named Gail Beeker was analyzing radio telescope data at Leiden University in the Netherlands when she detected something disturbing in the hydrogen emissions above our galaxy. A massive comet-shaped cloud of gas was plummeting toward the Milky Way at 700,000 miles per hour. Now known by her married name, Smith's Cloud, this cosmic projectile contains the mass of 1 million suns and stretches 11,000 light-years from head to tail, sculpted into its distinctive shape by ram pressure as it tears through the galactic halo. What makes Smith's Cloud particularly unsettling isn't just its enormous mass or catastrophic trajectory. It's the mystery of its origin. Currently positioned approximately 40,000 light-years from Earth, the cloud will collide with our galaxy's disk in roughly 30 million years, triggering an explosive burst of star formation that will birth an estimated 2 million new stars. But we cannot determine where it came from or what it represents. Spectroscopic analysis revealed the presence of sulfur in the cloud, definitively proving it's not primordial gas from the early universe. This chemical signature suggests three possibilities, none confirmed. First, the cloud might be recycled material, gas expelled from the Milky Way's disk by supernovae and stellar winds 70 million years ago, now falling back under gravity like a galactic fountain. Second, it could be the tidally stripped remnant of a small dwarf galaxy being torn apart by the Milky Way's gravitational field. Third, it might represent something else entirely, a phenomenon our models haven't anticipated. Scientists have attempted to trace its orbital path backwards through time, but gravitational interactions make precise trajectory calculations impossible beyond a certain point. Something containing 1 million solar masses is approaching our galactic neighborhood at catastrophic speed, and despite decades of study, we still don't know what it is or where it's been. Number 7. Przybylski's star. In 1961, astronomer Antoni Przybylski was conducting spectroscopic observations at Mount Stromlo Observatory in Australia when he discovered a star that violates the fundamental rules of stellar chemistry. Located 356 light-years away in the constellation Centaurus, the star designated HD 101065 displayed spectral lines that shouldn't exist. Przybylski detected the unmistakable signatures of technetium-99, an element with a half-life of just 211,000 years. He also found promethium, which decays even faster. Its half-life is a mere 17.7 years. The problem is immediately apparent. The star is estimated to be hundreds of millions of years old, possibly over 1 billion. The radioactive elements Przybylski detected should have decayed into stable isotopes long ago, yet spectroscopic observations confirm their presence at detectable levels. No known stellar nucleosynthesis process produces these elements in sufficient quantities to explain the observations. Even more disturbing, some researchers claim to detect actinium and possibly plutonium, though these findings remain highly disputed. Scientists have proposed several explanations, none entirely satisfactory. The leading theory suggests radiative levitation. The star's strong magnetic field and radiation pressure might selectively concentrate trace radioactive elements from the stellar interior into visible surface layers. But this mechanism struggles to explain the observed abundances. Alternative theories propose the star recently accreted planetary material containing these elements, or that unknown nuclear processes operate in its atmosphere. Some fringe theorists briefly suggested the most provocative explanation, that an advanced civilization might be using the star to dispose of nuclear waste or conduct stellar engineering. Mainstream astronomy completely rejects this interpretation, favoring undiscovered natural mechanisms. Yet decades after its discovery, Przybylski's star remains a chemistry puzzle that challenges our understanding of what elements can exist in stellar atmospheres and why. Number 6. The CMB Cold Spot. In 2004, scientists analyzing data from NASA's Wilkinson Microwave Anisotropy Probe made a discovery that challenges our most fundamental assumptions about the universe. Deep in the constellation Eridanus, they detected an anomaly in the cosmic microwave background, the afterglow of the Big Bang itself, the oldest light in existence. A region spanning approximately 5 to 10 degrees of sky appeared 70 microkelvins colder than surrounding space. This temperature difference seems minuscule, 70 millionths of a degree. But in the precisely uniform cosmic microwave background, where typical fluctuations measure around 18 microkelvins, this cold spot represents a statistical anomaly, with roughly a 1 in 50 chance of occurring randomly. When Europe's Planck satellite confirmed the finding in 2013, with even higher resolution, the mystery deepened. Something was fundamentally wrong with this region of space. Scientists proposed the most logical explanation: a supervoid, an immense underdense region where fewer galaxies exist. In 2015, astronomers detected exactly such a structure, a void approximately 1.8 billion light-years across, aligned with the cold spot. As cosmic microwave background photons traverse this void, they lose energy through the integrated Sachs-Wolf effect, arriving at Earth slightly cooler. Problem solved. Except it wasn't. Detailed calculations revealed the supervoid explains only 10 to 30% of the observed temperature deficit. The cold spot remains significantly colder than the void alone can account for. Alternative theories grew increasingly exotic. Cosmic texture defects in space-time fabric from phase transitions in the early universe. Or most provocatively, evidence of collision with another universe. In an eternal inflation multiverse scenario, what disturbs cosmologists most isn't just the cold spot itself, but what it represents. If this anomaly reflects something beyond standard cosmology, then our most successful model of the universe might be incomplete in ways we haven't imagined. Number 5. Steve. For decades, aurora photographers across Canada and the northern United States captured something peculiar in their images: ribbons of mauve and purple light stretching across the sky. often accompanied by vertical green structures resembling a picket fence. They assumed these were unusual auroral displays and thought nothing more of it. Then in 2016, citizen scientists from the Alberta Aurora Chasers shared their photographs with professional researchers, and the truth emerged. What they'd been photographing wasn't aurora at all. NASA scientist Elizabeth McDonald and University of Calgary physicist Eric Donovan led the investigation, utilizing data from the European Space Agency's Swarm satellite constellation. When the satellites flew through one of these mysterious ribbons, the instruments revealed something unprecedented: a narrow channel of superheated gas, approximately 25 kilometers wide, racing westward through the ionosphere at 6 kilometers per second. The temperature inside this ribbon reached 3,000 degrees Celsius, and it occurred at altitudes around 300 kilometers. The group jokingly named the phenomenon Steve, after a children's movie, before creating the backronym Strong Thermal Emission Velocity Enhancement. But the humor masked a disturbing realization: this atmospheric phenomenon had been occurring regularly for years, possibly centuries, and the scientific community had completely missed it. Steve wasn't caused by the same particle precipitation that creates auroras. It represented an entirely different process, one that contradicted previous understanding of Earth's magnetosphere. Scientists theorized the heating results from subauroral ion drift creating frictional heating, but models cannot fully reproduce the observed temperatures or the associated green picket fence structures. The phenomenon appears during moderate geomagnetic activity, visible to anyone at mid-latitudes who knows to look for it. We discovered an entirely new atmospheric process hiding in plain sight, announced not by satellites or universities, but by amateur photographers who simply paid attention to the sky. Number 4. Himiko Cloud. In 2009, astronomer Masami Ouchi was analyzing data from the Subaru telescope in Hawaii when he detected something that shouldn't have had time to exist. Using narrowband imaging to search for Lyman alpha emission from the early universe, his team discovered a massive blob of hydrogen and helium gas approximately 12.9 billion light-years away. The light reaching us was emitted just 800 million years after the Big Bang, during an epoch when the universe was still assembling its first large-scale structures. What makes the Himiko Cloud truly disturbing is its scale. The structure spans 55,000 light-years across, roughly half the diameter of the Milky Way, and contains the mass of 40 billion suns. Standard cosmological models predict that in the early universe, structures this large simply didn't have enough time to form. Gravity works at finite speed, pulling matter together over hundreds of millions of years. Yet, here was something enormous existing when the universe was barely 6% of its current age. Even more puzzling is what the cloud isn't doing. Despite containing enough gas to form billions of stars, Himiko shows minimal star formation activity. The massive reservoir of primordial material just sits there, glowing in Lyman alpha emission but refusing to collapse into stellar nurseries the way physics predicts it should. Follow-up observations with the Hubble Space Telescope and ALMA Radio Telescope revealed the cloud appears to consist of 3 distinct emission regions, suggesting multiple proto-galaxies in the process of merging. Scientists theorize this might represent an early stage of massive galaxy formation we've never directly observed before. The moment when separate clumps of dark matter and gas first come together to build what will eventually become a giant elliptical galaxy. But the exact mechanism preventing immediate collapse into stars remains unexplained. What cosmic scaffolding holds together something that should have already ignited into a brilliant stellar metropolis? Number 3. SDSS J1748-2446ad. In February 2015, Yebing Wu from Peking University announced a discovery that shattered our understanding of cosmic timelines. Using the Sloan Digital Sky Survey combined with observations from the Lijiang telescope in China, his team identified a quasar 12.8 billion light-years away in the constellation Pisces. At first, finding another distant quasar seemed routine. Then they measured its mass. The supermassive black hole at its center contained 12 billion times the mass of our Sun. The problem becomes apparent when you consider the timeline. This monster existed only 900 million years after the Big Bang. To reach 12 billion solar masses in the available time requires the black hole to feed continuously at the maximum theoretical rate, the Eddington limit, from the moment the first stars died. Even starting from a seed black hole of 100 solar masses, maintaining perfect accretion efficiency without interruption for 900 million years barely allows this mass to be reached. Any disruption in the matter supply, any period of slower growth, makes the observed mass mathematically impossible. The implications are profound. Either our models of black hole formation are fundamentally wrong, or this object began from seed black holes far more massive than standard stellar death can produce. Some theorists propose direct collapse scenarios, where primordial gas clouds weighing 10,000 to 100,000 solar masses collapse straight into black holes without forming stars first. Others suggest super Eddington accretion, feeding faster than theoretical limits should allow. operate in the early universe under conditions we don't understand? What makes SDSS J0100+2802 particularly unsettling is its luminosity. The quasar shines 420 trillion times brighter than our sun, 7 times more luminous than any previously known quasar. Something grew impossibly massive in impossibly short time, and now broadcasts its existence across most of the observable universe, a beacon announcing the presence of physics we cannot fully explain. Number 2, GRB 080916c. On September 16, 2008, at precisely 001245 UTC, NASA's Fermi Gamma Ray Space Telescope detected an event that challenges the fundamental limits of physics. A gamma ray burst erupted from 12.2 billion light-years away in the constellation Carina, and for the next 63 seconds, it released more energy than our sun will emit in its entire 10 billion year lifetime. The instruments registered the most powerful explosion ever recorded in human history. The numbers are almost incomprehensible. The total energy output reached approximately 8.8 times 10 to the 54th ergs, equivalent to 9,000 supernovae detonating simultaneously. Even more disturbing, the burst produced photons with energies up to 13.2 gigaelectron volts, arriving seconds after the initial gamma ray flash. These ultra-high energy photons suggest particle acceleration mechanisms operating at extremes we cannot fully explain. The leading theory proposes a collapsar, an extremely massive star, perhaps 50 to 100 times the mass of our sun, collapsing directly into a black hole. As matter spirals inward, it forms an accretion disk that launches ultra-relativistic jets, beams of matter and energy traveling at 99.9% the speed of light. When these jets punch through the dying star's outer layers, they produce the observed gamma ray burst. But here's what troubles astrophysicists. Converting the kinetic energy of a collapsing star into gamma radiation, this efficiently approaches or exceeds theoretical limits. The jet formation mechanism must be extraordinarily refined, the energy extraction nearly perfect. Some scientists question whether known stellar death processes can account for the observed power output, suggesting either exotic physics in extreme gravitational fields or gaps in our understanding of how massive stars die. When the universe's most violent explosion challenges our models of maximum possible energy release, what does that reveal about the events we haven't yet detected? Number 1. HESS J1748-2446ad. In 2022, astrophysicist Viktor Doroshenko from the University of Tübingen announced a discovery that violates one of physics' most fundamental principles. Using X-ray observations from the XMM, Newton, and Chandra space telescopes, his team measured the mass of a neutron star in the constellation Scorpius, approximately 8,000 light-years from Earth. The result should have been impossible. The object contained just 0.77 solar masses. This number represents an existential crisis for stellar physics. The Chandra-Sekhar limit, established nearly a century ago, defines the minimum mass required for neutron star formation at approximately 1.17 solar masses. Anything lighter should be a white dwarf, held up by electron degeneracy pressure. Anything heavier overcomes that pressure and collapses into the ultra-dense state of a neutron star, supported by neutron degeneracy pressure. This boundary has been validated through countless observations and represents a cornerstone of our understanding of stellar death. Yet HESS J1748-2446ad exists. With a radius of just 10.4 kilometers, it displays all the characteristics of a neutron star: the temperature, the emission spectrum, the compact size. But its mass falls far below the theoretical minimum. No known supernova mechanism can produce such a low-mass neutron star. Scientists have proposed exotic explanations: strange quark matter composition, mass stripping by a vanished companion star, or unprecedented collapse dynamics, but none fully explain the observations. What makes this discovery truly unsettling isn't just that it violates established limits. It's that it forces us to confront a fundamental question. If our models of stellar death are wrong about minimum mass limits, what else might they be wrong about? This small sphere in Scorpius represents either an entirely new class of stellar remnant or evidence that our century-old understanding of how stars die requires complete revision. Either we've discovered something that shouldn't exist, or we've been fundamentally mistaken about the rules governing the universe's most violent transformations.